Sciences Alumnus of the Year Award in recognition for all the things he's done for the optics and photonics community, as well as the incredible support he's given to our college. So Jim is Vice President and General Manager of the Civil Space and Technology Strategic Business Unit at Ball Aerospace, which is based in Boulder, Colorado. And there he's responsible for acquisition and execution of programs for civil customers that address science and technology development objectives. He's had other leadership positions at Ball, and most recently, before his current position, was Vice President and General Manager of a unit they call Tactical Solutions. And he's also served as Director of Program Execution for Advanced Technologies and Products Business Area. Prior to Ball, Jim was in technical and management positions across the industry and science community, and that includes in the science sector, leadership positions at the Gemini Observatory and at the National Solar Observatory. And earlier in his career, he worked at a bunch of companies such as Phase Shift Technologies, Hughes, TRW, Census Corporation. Most importantly, Jim is one of our own. He got his master's degree in optical sciences. He got his bachelor's degree at some other college here in Rochester. I'm not sure what that is. But he also has a MBA from the other college here at the University of Arizona. And he's a fellow of SPIE and a lifetime member. And he's served on the board of directors of SPIE, and he's been chair of several conferences, and very, very active in committee and advisory roles for the optics and photonics and astronomy community, serving on organizations such as for the James Webb Space Telescope and other large projects like that. And as I mentioned, for the university, he's been very active. He serves on the College of Optical Sciences Development Board, and also on the a lot of leadership positions as an alum of the Eller College. So most recently, Jim and his wife Michelle, who I hope will be with us tomorrow,
she will.
Established the Jacobus. Jim is short for Jacobus, and Michelle Oschmann Scholarship in Optical Sciences and Business Leadership. So it's a unique endowed scholarship for students who are not only interested in optics and photonics technology, but in taking their technology into the business world and developing some business experiences. So without further ado, let me welcome Jim. Let's give him a hand. I guess you could use this mic.
I have a mic. They have me wired in.
Thank you.
Thank you, everybody. Pleasure to be here. I have a talk here that is pretty high level, lots of pictures, no equations or tests afterwards. I was asked to give something that challenged the technical minds of the students and faculty, and said, I can't do that anymore in my position, but I hope to give you a sense of the types of things we do at Ball in the optics arena. I'm not going to cover everything here. I'll then go and talk a little bit about U of A and Ball relationships, including a number of alumni that we have at Ball Aerospace, and some things that we're in discussions with about going forward in the future, in general, the types of things, if you will. So with this, the clip that's been playing there, this is courtesy of the NASA and the Space Telescope Science Institute. These are taken from real images with various instruments on the Hubble Space Telescope, and then animated and made to look in kind of 3D as you fly through it by the Space Telescope Science Institute. And the relevance here to Ball, which you will see later on, is that almost all of these images in this clip, and most images you see from the Hubble, were produced by instruments that were largely designed and built by Ball Aerospace in Colorado. So that's the relevance there. And I'll apologize, there's a little bit of logistics in going back and forth between presentations here. So there's a couple of other movie clips that I'll have to stop now and then to get them right. And I am hoping that there's plenty of time, and if you have interest, just to talk about, if you want to ask me any questions about Ball or what it's like to work in industry as an optics person, I'd be glad to share my thoughts and get your views on that too. Okay. So I hope to give you a flavor based on our civil business. By civil business, think primarily NASA, though it's not exclusively NASA. Science-based examples of projects where we've had either a small part or a large part of the optical systems involved with these platforms. It's going to look at satellites, many satellites we've built that are looking down at the Earth for various reasons, and I'll show you some examples there, and then looking outward as we go forward. But to start in the beginning of Ball, going back to the very earliest years of Ball, Ball Aerospace was formed in 1956, and I'll show an example of the type of thing they worked on then, but this cover slide gives an example of things that were worked on in the 60s and 70s, from components like fine and fast steering mirrors. This one on the left was something called a relay mirror experiment, having to do with bouncing lasers off of satellites. The middle one is the orbiting solar observatory. I have another slide on that. And the one on the right is a telescope payload for the Skylab. A lot of you may not know what Skylab is, but think the predecessor or father or great-grandfather of the International Space Station. It was America's first space station up in space. And so there were instruments on that. The ones Ball were involved with were primarily for solar observations, but I'll get into that a bit. In the absolute beginning, what we really got into at the beginning of what was then called, as Eustace Derniac knows, because he used to work there, Ball Brothers Research Corporation. 1956, it was started as basically a tech transfer offshoot from University of Colorado Boulder, the LASP group there, Lunar and Atmospheric Sciences. And they were doing upper atmospheric research with sounding rockets with instruments on the rocket looking at either the sun or stars up here. And basically, once it's launched, the cone would come off, and this mechanism would de-spin. These rockets spin as they go up, so this would counter the spin, so you could look in one direction with an instrument to make a measurement there. Developed at LASP. They started producing a number of them. Story goes, the university said, are you researchers or are you production? And they decided, in conjunction with one of the founding family members that owned Ball at the time, a guy by the name of Ed Ball, one of 5 brothers running it, he had bought a small business because he was tired of food and beverage packaging. I'll get back to that. And he met them and said, oh, it sounds like you have a product without a company. I have a company without a product. And that's what formed Ball Brothers Research Corporation in 1956. His brothers saw him making money right away, so they brought him into the corporation. This is why a Ball is a food and beverage packaging company. It's not an aerospace company. 10% of it is a wholly owned subsidiary now called Ball Aerospace. Most of you, though now, because some of the faces I see in here, not all of you, won't recognize the bigger part of Ball is known by a lot of people of producing glass jars for canning preserves. We don't make those anymore. They are made with our logo on them, but we're now one of the world's largest manufacturer of aluminum cans and steel food cans and aerosol cans, and it's a global business, 10 times bigger than aerospace. But the interesting part was the aerospace here, and it's grown pretty much organically ever since then. In the 60s, the orbiting solar observatories, we built 7 of these satellites. These were NASA's first orbiting satellites for science measurements. On there were a number of orbital observations first, the first orbital observations of the solar corona. measuring complex magnetic fields, and measuring various other parameters that help predict solar flares. I have a little bit more on the 60s and 70s here coming up in a second. These are all primarily some form of spectrometers that were on board. By the way, those sounding rockets, the optics were really large, 1 centimeter. Here they're a little larger, but not a lot. Late 60s and into the 70s, we built 4 instruments that went on the Skylab space station there. The instruments are listed there, all forms of spectrographs. They're basically one coronagraph. The picture on the left is one of the instruments enclosed there with a visitor. This was a project through Marshall Space Flight Center in Huntsville, and that's Wernher von Braun there inspecting the instrument at Ball in Colorado, considered the father of American rocketry, if you will. Now, the interesting thing, those instruments, 3 of them used film. So this is an astronaut either installing or taking out a film canister from some of those instruments there. So no detectors and transmitting the data down to the ground, film. Anyone still familiar with film here? So now that gives you a little bit of the beginnings. I'm going to give just a few examples of Earth observing from Ball Aerospace. And I'll cover some examples. This is a commercial satellite. I'll show you some images from that. We built it for a company called Digital Globe that's in Longmont, Colorado. We helped form that company. If you pull up a map on Google Maps, most of those images come from a Ball-built satellite, though some of them, the payload or optical system, is built by Excelis or their former Kodak. So we work with them on that. The earlier ones, we built the payload and everything there. The middle one is operational land imager. I'll show an example of what that is and what it does. And then this is a LiDAR-based system looking at clouds and aerosols from orbit, called Calypso. Some examples of what you're looking for. The Calypso system, again, orbiting around the Earth in a low Earth orbit, is then mapping out across the globe, looking at clouds and aerosols, smoke, things like that, basically Earth science research. We do quite a few of these types of programs at Ball and have historically. Calypso was supposed to be a few-year lifetime, and I believe it's on 13 years running, and it's a pulse laser, and it's at about 5 billion shots now, far beyond the life it was expected to operate at. On the right, QuickBird is one of our first commercial satellites that we did for Digital Globe, where we did the optical system, 60-centimeter aperture on this one, not 1 centimeter that I mentioned earlier, so it's gotten a little bigger here. And this is an image of it finding, this happens to be an aircraft carrier in the middle of the ocean, pretty good resolution image. The newer Digital Globe satellites have even better imagery now. This is what goes into the Google Maps. Now, those images are sold commercially across the globe and to the U.S. government for various purposes besides Google Maps. Another use of our commercial imagery through Digital Globe here, this is an example. When there is, unfortunately, a disaster here and there, these satellites are being used more and more to help very quickly do damage assessment where the areas that were hit, what is the extent, much easier to see where to go with fairly high-resolution images from space rather than to drive around and try to map that out. So this is in Moore, Oklahoma, with a tornado in the beginning of 2013, before and after. So they track forest fire types of effects to tornadoes to what did your, on Google Images, sometimes the images are a few years old, so if you built a new house, you may have an empty lot showing in the image there. But you pay more money, you get more recent images. So. Another couple of examples on the Landsat, where we built what's called the operational Landsat imager, the eighth in a series of a satellite that's been mapping around looking at Earth properties from more of a macro scale. This is not a high-resolution image. The pixels are on the order of a kilometer or so, but looking over wide areas, and it's looking for long-term changes in the various aspects like vegetation and things like that across the globe. But it also, on a macro scale, this picked up that this is a forest fire from a few years ago in New Mexico over a very large area. So it's used for a variety of purposes, but it can, help monitor drought conditions and things like that. The Landsat program has been making these measurements across the globe for 40 years. And so they're on their eighth satellite to keep that constant, what is changing across the globe. The Sonomi NPP and joint JPSS, or Joint Polar Sensor System, are the latest low Earth weather satellites that NOAA and NASA has put up. We built the satellite bodies. There are 5 instruments that we integrate on the satellite. One of those instruments we built, which is an optical instrument, that's an ozone mapping profiler suite. So it's measuring, and this is an image of a compiled data as it circles the globe, building up a 3-dimensional image of ozone in the atmosphere. Example, like the hole over the, is it getting bigger or smaller in the Antarctic region? Good news that's been in the press for actually a couple of years, though they say it's slowing down, that hole has been closing up, which is good. Another fun from our commercial imaging, the images on here, this is a series of images pieced together from DigiGlobe, from the QuickBird satellite that we built the optics for that one, and the rocket that it's imaging is WorldView 3, 4 satellites later, 1.1 meter aperture. Excellus in Rochester built that payload, and we integrated it all on our spacecraft. So it's kind of the father seeing the son coming up here. So now looking outward, give you a few examples here, and this is the Kepler telescope. I'll show more on that. Deep impact, and instead of Earth imaging, Mars imaging. We call it the HiRISE imager. This is orbiting Mars, collecting images of the surface of Mars. No Google Maps of Mars yet. I'll show you an example that might lead to, could be interesting though. Oh, they do now. So it's probably using these images. See, I'm learning something here. I like that. So with that, an interesting, relatively recent image from that imager looking at the surface of Mars that Ball built. This is the Curiosity rover. It is the most recent rover that landed on Mars. Going down through its atmosphere with a parachute, we managed to capture an image of the rover as it's descending through the atmosphere from the imager we have around Mars there. Now here I'm going to give some examples, and this isn't perfect, it's going from my memory, but an important point that I wanted to make sure you knew here, the principal investigator for this and where the program was run out of for this instrument, for the imager that produced these images, was the University of Arizona, the lunar planetary people across the street. Howard McEwen was the PI on this, that we worked for him on that program. There might be a few more examples of things like this. Deep impact I mentioned. Here's an image of a satellite smashing into a comet on purpose. The satellite was really a 2-part satellite. It was built entirely by Ball Aerospace. Our first deep space mission went out to this comet, separated, had an impactor go with a camera as you're going into the comet. Purpose was to create some dust, create a crater, and then the host spacecraft with imagers and spectrographs on it looking at the chemical makeup of the comet from the surface. Surprising results from that. It blew up a cloud that you couldn't see through, and it was almost all silica-type, sand-type material. That is not what was expected. On the right side, a deep space mission that we're part of, it's still going on, where we built a multi-spectral camera for the New Horizons, which is on its way to Pluto. And I should have made a little joke and X this out and put planet, but Pluto is no longer a planet, I guess. But there's still ongoing debate. So that will reach its target in July of 2015, this next year. I believe it was launched in around 2007 or something like that. So quite a long ways out there. Interesting little side note on that, as this flies by Pluto, collects its images and some spectrum, mission over, original mission over. Well, if the spacecraft and everything's still operating, they always like to, well, what else can we do with it? Well, it's going beyond Pluto. It can't stop. It can't turn around. Can't do anything else there. But Pluto is now considered a Kuiper Belt object, where there's a huge number of, smaller rocky bodies beyond the orbit of Pluto there, called Kuiper Belt objects. Can we identify one or two ahead of time that are close enough to the path that New Horizons could do a flyby and also study that? Only in the last few months, using the Hubble Space Telescope, they have now found 2 or 3 viable candidates that it can fly through. So it does look a high chance they will extend that mission. Say a little bit about Kepler. I showed a picture of the spacecraft there. For that, we built the spacecraft and the payload, which is an imaging photometer. It doesn't have to have the greatest image quality on it. What's really important is that very low, relative low noise and stable, because what it's looking for is a planet transitioning in front of its sun, blocking some of the light. So you're looking at a light curve on every pixel on a 95 megapixel camera, basically, for that small dip, ideally looking down to Earth-sized planets around Earth-like stars, but it's captured a whole range of things there. And it needs to have a relative sensitivity of kind of 1 × 10⁻⁸ to reach Earth size. Recently, they have found an Earth-size planet. Now, we don't know if it has water or anything like that yet. So it has met its goal in its original mission here. And this is just a graphic produced by NASA earlier, giving kind of the relative idea. You see some tiny planets compared to large stars and so forth. But there's been almost 1,000 confirmed planets. Now, they aren't confirmed until you get at least 3 revolutions to see a periodic dip. And you follow up with other assets like Hubble or ground-based telescopes to then, once you know where to look, it's easier to help confirm whether they're planets or not. They still have a lot of data going through, but there's over 4,000 other planet candidates. This changed the paradigm of what most astronomers were thinking in our galaxy, that from it is a rare occurrence. Used to be thought of that planets around stars would be a rare occurrence. Now it's rare if it doesn't have not only one, but multiple planets around other stars. So it's really changed the thinking just in the last few years of this. With that, I did want to mention, so here's one piece of test equipment that I can't show all the details, but that's a 1.5 meter off-axis parabola up there. There's also a 1.5 meter flat down near the bottom. It's a piece of test equipment that we took the whole Kepler spacecraft and photometer, put in to provide a point source from infinity through the off-axis parabola for the purpose of testing Kepler end-to-end in a cryo vacuum chamber at Ball. And these optics were produced at Optical Sciences at University of Arizona originally. So this is a case, rather than, like Alfred McEwen contracted to us, we are his teammate industry partner to build the Mars imager. This is a case where we contracted the university to provide some critical test equipment to help confirm that Kepler was meeting its requirements before we launched it. A couple of other side notes that isn't directly optics. we have a lot of cryogenic capability, including cryogenic optics. But our first real experience in that is we came up with an idea and were able to work on what was called HiRISE, an infrared all-sky survey satellite. And our role was the cryogenic chamber to cool the detector and the optics here. I wanted to mention this for a couple reasons. One, that included Dr. Frank Lowe at Stewart Observatory, so another A here. And our experience here, it worked so well and lasted so much longer than expected and met all the thermal requirements. They asked us to build another one for a cosmic origins background experiment. This helped John Mather and George Schmoot win the Nobel Prize. A little bit on Hubble. Ball's built a total of 7 instruments for Hubble. And when Hubble was first launched, there was a problem. The primary mirror was, as someone has quoted, perfectly polished to the wrong shape, spherical aberration in there. That's the most technical I'm going to get here, by the way. And we at Ball ended up having the system's responsibility to building the corrective optics that corrected that spherical aberration and refed the beam into 2 of the other instruments on board Hubble during the first servicing mission. That led to 20 years of work for us on Hubble, building other instruments for Hubble, total of 7. All of the instruments currently on Hubble were largely designed and built in Boulder by Ball for various people under people like Jim Green at University of Boulder, Cosmic Origins Spectrograph. That's a picture on the upper right here. Wide Field Camera 3, showing some of these star-forming regions here. These types of images are often in the press. And Nick Moss, near-infrared camera here. Nick Moss, another U of A, the PI, was Roger Thompson at Stewart Observatory on this. So here is where I have to remember how to get the video back here. F7. So I'm going to show, this is kind of a commercial thing that Ball did about our involvement in Hubble. It's a little less than 2 minutes, and I'm close to the end here.
Travel to distant galaxies 500 million years old. Gaze at the youngest and most distant objects ever seen. Marvel at black holes in the center of galaxies. Because in one moment, imagination and innovation brought us the Hubble Space Telescope, creating the most profound shift in our understanding of the universe since Galileo. Led by NASA Goddard Space Flight Center, private companies, universities, and government organizations work side by side to build an observatory like no other. But before it could bring us stunning images like the Eye of God, eyeglasses had to be made for the telescope. That's because Hubble was launched with a defective mirror, returning images too fuzzy for astronomers to study. The Hubble team went back to work, and 3 years later, NASA sent astronauts to fix the telescope, installing a corrective optics instrument called COSTAR, built by Ball Aerospace. A decade of discoveries had passed when panic struck the astronomy community once again. NASA declared future missions to Hubble too risky after the Columbia Space Shuttle and its crew were lost during Earth's re-entry. But the public outcry over Hubble's premature demise proved to be too much, and in 2009, NASA agreed to send astronauts back to install 2 more Ball Aerospace imaging instruments, making Hubble more powerful than ever before. Aboard Starship Hubble, we've confirmed the universe is some 14 billion years old. Learned the universe is moving away from us faster and faster due to dark energy, and traveled 12 billion light years from Earth. Ball Aerospace has built 7 imaging instruments for Hubble, enabling extraordinary science that has helped change the course of astronomy forever. We travel to distant galaxies.
You don't need to hear it twice. That's enough on Ball commercial there. I will say on these programs, huge involvement from multiple NASA centers. The work on Hubble, all of it was under Goddard Space Flight Center, but multiple NASA centers, and very close relationship with Lockheed Martin, who is the prime contractor for all this and involved in all of the servicing missions there. And just to be clear, when it says we made these discoveries, it's we, the astronomy community, not Ball Aerospace. We build the instruments, not the science that comes out of them. Got to get this back in the... Uh-oh. Apologize for this. It's not exactly seamless, and I didn't do it quite right. So there are 4 major observatories up there right now called NASA's Great Observatories. And I'll just say Ball had either small or large piece of all of it. Spitzer is a high-quality infrared telescope where we did not only the cryogenic cooling in tanks, but the cryo telescope and some of the instrumentation on there. Chandra, some of the instrumentation, and a little bit on the Compton Gamma Ray Observatory here. And of course, a reminder, if I know U of A was involved in that one, apologize if they were involved in the other ones. A little bit looking to the future, just a couple of examples. And I'm going to start out with our, for us, the most exotic, if you will. We have just finishing up a contract for a lab demo of how we might apply thin membrane diffractive, transmitting diffractive optics to form a primary mirror rather than reflective telescopes. Now, this would obviously be very narrow band, so it would be for certain niche science or various applications. This is one of they call the DARPA hard type programs, but the idea was to build a segment of what could be a 10 to 20 meter deployable aperture in space that at a geo stationary orbit could get about a 1 meter resolution on the Earth. That was the intent of the DARPA lab demo, and you build and demonstrate some of the technology pieces of that, not actually build the whole thing and launch it. But that was the envision for that. There are possible science applications in Earth science. If you only wanted to look for a few atmospheric lines or pollutant lines for Earth science, or if you wanted to look for signs of methane and water, there might be signs of potential life on another planet, and you want a dedicated mission just for that with a very low cost, we believe, and lightweight system. This is an alternative. So those are the few of the potential applications. So these are very thin mylar with, as U of A and Stewart Observatory does a lot of diffractive optics called computer-generated holograms for optical testing. Well, basically it's the same. You're writing a pattern in here to cause it to diffract, to form an image behind these individual segments, and then in the back spacecraft, which I'll show you an example, an artist concept, what that might look like, is where you would combine all of these, make any corrections, do some color correction to get a little bit more bandwidth, and form your final images. So I will try again to show a video. This one doesn't have sound in it. This is an artist concept of what it might look in space deploying from a large spacecraft. All looks like a very compact, but let me blow this up here. First extending basically the objective lens to about 140 meters in front of the spacecraft if it were a 10 meter aperture kind of thing. And so we had to demonstrate mechanisms that could do this, subscale of this, that were lightweight and consistent with this design. Then, actually by disabling some latches and having built-in tensions into hinges, the upper part, when those bars release, would just start to deploy on its own to the full primary mirror, objective lens. We do many more mirrors than we do transmitting optics at Ball. Then you do have to be concerned about the alignment from here back to the the host payload where you're going to do the beam combining. So there would be potentially some laser type ranging things to help with alignment. You'll see that little animation of maybe some tip and tilt on individual segments, but there's also active optics on the back on correcting it in a small package to deliver the final images. And I need to let the credits go to DARPA on this here. So. And Tom, I think we brought you in to see this at Ball, right? Last video. So let's see if I can transition better this time. Probably not. All right, a couple of newer things that are destined for science, not always in space, though. For Ball, we thought about for many years maybe participating in the ground-based astronomy community, helping on large telescopes. But we have historically done very little to probably no hardware for telescopes. But last year, we did win a contract to build a part of the Large Synoptic Survey Telescope. The part we're doing is in partnership with Arizona Optical Systems, Jim Burge, building 1.6 meter corrector lenses, two of them, L1 and L2. In Tucson is where the optics are going to be ground and polished, and Ball is designing and building the composite structure to hold these, integrate and test down here in Tucson. And then on the right, the James Webb Space Telescope, we're responsible for all the optics. Now, we don't manufacture that, but we design the details, and these are beryllium optics. We brush weld them to get the materials. ATK and others for helping with forming the blanks and then ending up at polishing at Tinsley, but testing them cryogenically at Marshall Space Flight Center. These mirror blanks cross the country multiple times in the steps to lead to the final mirrors. The mirrors operate on orbit. These are 6 of the mirrors in a cryotest facility down in Huntsville, Alabama at Marshall. They're polished in California. They're polished at ambient temperature. When you bring them down cold, they do deform quite significantly. So we would then bring them to Huntsville after we integrated some of the support systems behind it. We'd take them cold. We'd measure the deformations, creating a hip map that you would take the inverse, take it back to Tinsley, and then polish the inverse of that, bring it back to Marshall, and see if you met the requirements. A lot of debate early on the program, on various committees with people like Jim Wyatt, who's in the back here, and other people from U of A, on how many cycles it would take to converge to the spec for those mirrors going back and forth across the country. I think our engineering development unit, we did 2 cycles on that. Every flight mirror got it right the first time. The mirrors are all done, and they're waiting to be integrated for the rest of the telescope. And we also did the secondary mirror and a tertiary mirror and fine steering mirror in an assembly at Ball. We designed the support systems and hexapod positioning systems, electronics to drive these, all of which have to operate down to 20 degrees Kelvin. And we developed all of the algorithms for sensing, looking at starlight, the phasing and control of the optics to align everything. And each of these mirrors does have a 7th degree of freedom. There's an actuator in the middle to bend or change the radius of curvature to match that across the total primary mirror. So all of that's done and ready. We're now working some test equipment and helping in the integration and test currently at Goddard Space Flight Center. And on both of these, though it's not a direct involvement, as you know, you should know, U of A certainly with the LSST, but also the primary instrument critical to the observatory working for James Webb is led by Marcia Ricci at Stewart, Lockheed Martin, building that instrument for them. We built a few of the optics that go in that instrument that are used to measure the wavefront and phasing. So not a direct contractual relationship, but it's how often these projects that you form a partnership and you still have to work across those lines very well. I'm going to change gears quite a bit here now. I think I still, pretty good on time. And we can come back to any questions on these. I can't guarantee I have the answers, but I can try. I'm going to talk in a little different flavor about our relationship with the University of Arizona, what it has been for us. It's only a couple, 3 slides coming up, but just kind of information on how we view the relationship in different aspects than just these projects here. At Ball Aerospace, and this should say Ball Aerospace, we currently have 36 U of A alumni at Ball from a large variety of departments or degrees. The largest segment, about 40%, College of Optical Sciences here. Now, if you added this 6 plus 19 plus 19, I was going to test you, but I told you I wouldn't test you, adds up to more than 36. So I believe it's about 6 of these people have multiple degrees from University of Arizona. The one thing that I found in putting this together, I did not know until I put it together, was I don't know what that says. Maybe we needed help to have all these success on these instruments. Teamwork is involved, and human relations are as important, if not more so, often on these high-tech programs that require large teams of people. I can't say that's why we hired someone with a psychology degree, but I'm making that up. Ball Aerospace total employees, by the way, is about 2,800, and what we consider optical engineers, including detector people, is about 122 currently at Ball. If you talk about people who work on optical systems and mechanical, software, electronic, it's hundreds and hundreds. It's a big part of our business here. And just for fun, this is another digital globe image from QuickBird, the one where we built the optical instrument. The 50th anniversary of Ball Aerospace, not a few years ago here. I think we're at 58 now. This is a blue tarp in the parking lot with Ball employees with white shirts and baseball caps. So on to the U of A involvement. This is more, not a detailed list, but our most recent employee from University of Arizona, I would believe a lot of you in the room know, is Dr. Laura Coyle. She started with Ball in October. We've already made her give one of these types of seminars to our staff, talking about optical testing. She did a great job. She's working on a number of internal research and development projects, and will likely be involved, depending on how we go forward, on some ground-based optical things. And she'll be working earth science, space science, and who knows what else. But only 2 months. We haven't scared her off yet. Very good, excellent recent employee here. I believe she was a... Yes, that's right. So we're very glad to have Laura come and join our team here. I'll mention this more from a personal perspective, but I have Ball support in this. The scholarship that Tom mentioned there from my wife and I, that was, I do want to say, to make it a fully endowed scholarship, that was also leveraging the generosity of Jim Wyatt there in the back on one of his efforts to help get the rest of us to contribute a little more. And our first recipient, when we were partially funded at the time, some of you may know, he's actually physically resides working up at Ames Space Flight Center up in San Jose area. Kevin Newman is the first recipient. This is something picked by Tom and the university, not myself, but he is, we don't have anything to do with that, but I've met him, and we now have an ongoing dialogue of where we might collaborate on things like coronagraph for future endeavors looking to get the image Earth-sized planets as the goal, is one of the long-term goals of NASA on the science side. So we don't have a definite role in that, but these are the kinds of things when we make these connections, we'd like to see where can we help that would be mutually beneficial. And if it isn't mutually beneficial, we'd rather give you advice of what other company to talk to or what other university to partner with. But from a personal standpoint, thrilled here. What helped me fund this, though, is Ball contribute a portion of what we contributed through matching funds. Very generous company when that, as far as that goes. When employees donate money to any cause, they do 100% matching up to $5,000. So, Tom said I'm on the development board here, trying to work alumni relationships in a number of regards. I've been involved in committees with a lot of U of A people that touch on SPIE that I've been fairly active in, and Eugene Arthurs is here in the background here from SPIE. So I'm always glad to try to poke to get people working together. Not always successfully, right, Eugene? And various projects. So I gave many examples where we work for the university as a major industrial partner to design and build difficult space instrumentation. We are in discussions for future competitive endeavors to do the same thing. I don't think it's appropriate to say with who, but with people that we have dealt with at the university here. So we're looking forward to that. We're always looking for more opportunities to do that. They could be other forms of partnerships. Like I've mentioned, we have contracted the U of A to build optics for test equipment. So we're also trying to feel out where we can team with U of A to go after other programs where, depending on what they are, we could be in the lead, the university could lead. It's whatever makes sense to go win that work. So that's something of ongoing interest. And then potential R&D collaborations. Now, that's a broad area. We do not fund pure research. It has to be something that aligns to where we think we might go or have a chance to go. And it could be from, let's do a joint, what we call IRAD, internal research and development. You do your own thing, we do our own thing, but our interests are aligned and no money changes, but we work together, and together can we do more and propose as a team for the next steps to win some money from NASA or whatever, to it's not out of the question for us to send some of our research and dollar money to the university. There we contract with other companies to buy materials and things like that. We could do the same thing here. Down to, without as many constraints, something that I'm trying to have us look into and open to ideas, small funding without any real strings attached, but ideally something that aligns potentially to our interest for if you have, let's say, at an undergraduate level, if you have things, I think I was told you do have something akin to a senior research type project. This is something we do at CU Boulder quite a bit, but there's no reason why it can't be done with any university, where you have some project that you're getting credit for. You need a few $1,000s for materials. If it aligns at all to Ball's interest without any strings attached to that, Ball owns it kind of thing. Now, we want to get into it for the relationship, see where it goes. That's a possibility. It's not a formal process or anything yet. It's grown through relationships at CU, and I hate talking about CU when I'm in here when Arizona's going to take care of them Saturday night on the football field. I will be wearing Arizona attire for that, and I have gone to CU Arizona games in Colorado wearing Arizona attire, and I'm still alive.
CU football sucks.
Well, they got all excited about joining the Pac-10, now the Pac-12, and I couldn't resist. Sorry, this is a little diversion, but I said, Pac-10 just got tired. They want someone new to whip up on there. So They used to, a long time ago, have a very good football team. For a long time, no, it hasn't been good. But with them, because we're so close, and Ball Aerospace, Ball Brothers Research, now Ball Aerospace, grew out of CU basically, we have over 400 employees with at least one degree from CU. It's a very close relationship. We have engineers. It's not managed by the company that are on boards of different, advisory boards for departments all over engineering in particular. And so when, a former student who is on the mechanical engineering advisory board sees some interest from a student on some mechanism that we could use at Ball, oh, can you use a few $1,000s? The connections are made. And so how can we do that? It's a little harder because it's more remote, but these are the kinds of things that I'd like to look at and open to ideas and try to use some of this group of people, so it's not all flowing through me, to help instill a closer relationship with the U of A and optical sciences. So this is a list. Don't expect you to memorize it all, of our current U of A employees at Ball Aerospace. This is a subset. Almost everyone in here is at optics on this particular picture. I have to be careful saying it's an alumni at Ball Aerospace, because I did find one Ball corporate person who is a U of A alumni history major. I'd be rather looking more forward at Ball, though I gave you a bit of a historical perspective. So I'm open, we're open to ideas. Where does it make sense? We do not have a lot of money to invest in things, but we want to do things smartly and where it makes sense. And so with that, there's plenty of times for questions, and I have a few more just pretty pictures if you're shy.